Assalamu alaikum. Welcome to this session. Uh, in this session, we'll be talking about another perspective of applying machine learning algorithms in the practical context. More specifically, we'll be talking about different evaluation measures uh, in this session. So far, we have studied two types of algorithms. One category is of regression, other one is of classification. So our discussion of evaluation metrics is primarily divided with respect to the application context. So let's start with this question that why do we need to have evaluation metrics or measures in place? Because we want to measure performance of a model which we might have trained on unseen data. So primarily we are interested on the robustness or reliability of the model in the practical context if the model is deployed in a real world scenario. So how good or reliable would that model be to predict the desired outcomes. And for that purpose, we talked about this thing in our previous session as well, that we commonly use test data. So unseen data essentially represents the test data in our context. So we'll be using test data for different models to evaluate their performance. More specifically, we are interested in answering this question that how good are your predictions compared to the ground truth. As discussed at the start, that our decision of choosing a particular metric is essentially dependent on the kind of task which our model is supposed to perform. Okay, let's start with the quick review of the types, because based on the predictions or the nature of the predictions, our evaluation measures will adjust accordingly. So the first category of learning task whose evaluation measures we are going to talk about is regression. And I'm sure you are able to recall that regression essentially predicts the continuous values. For example, if you have to predict price of a vehicle based on some parameters like make and model of the vehicle, current condition of the vehicle, brand of the vehicle, seating capacity, etc., etc. So based on all those things, we can make a model which should be able to predict price of the vehicle. Same way, we might be interested in forecasting temperature using some input data. So y over here is a real value, which makes up the task of regression. The second category is classification. So we are interested in predicting a discrete label rather than a continuous value. So number of classes are always finite in the classification setting. In a binary classification setting, it might be 0, 1 or positive or negative examples, and it could be a multi-class problem. So we'll in the context of evaluation metrics, we will be primarily talking about binary classification, but we can always extend the idea of evaluating a binary classifier to a classifier of multiple classes. So the first measure which we are going to have a look at is for the regression tasks, and we are actually familiar with mean squared error, that we compare the ground truth with the prediction. We take the square of the error and we sum up all errors, and then we take the average. So the major contributor over here in the context of error is this square term, right? So if error is large enough, then its square is going to be larger enough. As compared to the test examples where error is relatively small, so their squares are going to be smaller as compared to the examples which are inducing more errors. So the basic idea behind choosing mean squared error as an evaluation matrix in the regression setting is that we are interested in penalizing large errors more heavily. So because each error is getting squared, so that square is going to contribute more in the overall error. And like mean squared error is a very good choice for the training purposes as well. That's what we saw in the context of gradient descent. So the key property is that this is sensitive to outliers, and that is what we need to keep in mind as a machine learning engineer. What does that mean? When we say it's sensitive to outlier, that means that when we say there is a prediction which is, let me try to uh, draw a quick example over here. So here is X, Y are the predictions, and we have different data points somewhere over here, and we might have fit some linear model around it, somewhat like this. Sorry for the again poor drawing, but by outlier we mean that there is uh, a point over here which is an outlier, which may be noise or like invalid data point collected or something like over here. So our model is this orange line, right? So whenever we try to predict something for that x, so that will be over here, and the magnitude of error is going to be reasonably large. Its square is going to be further large, and same goes for something over here that for this kind of x, our model is going to predict some value over here, but the ground truth is here. So the error is reasonably large, and square is going to be uh, larger, further larger. So in that context, that will be having a heavy contribution in MSE, and that might be giving us an illusion that the model's performance is poor because the error or squared error induced by the outlier is essentially going to dominate the mean squared error value. So that is the kind of thing which you need to keep in mind. So having an exploratory analysis or exploratory study of the data is always useful. As we go along, we might be having a discussion about how to figure out whether there are outliers or not. But like in general, MSC has sensitivity to outliers. It might not be giving us uh, the true picture of the performance of the model if there are outliers in the test. But at the same time, it is good enough. It gives us, if there are no outliers, so it gives us uh, larger squared errors where whenever there's a prediction which is off from the ground truth. So root mean squared error is square root of MSE, and it is preferred in practice because when we take the square root of MSE, we are back into the units of y, so it's easier to interpret. One more evaluation metric for the regression problems is that we don't take the square of the error, but instead we compute the absolute value over here, absolute value of the error. The deviation from the ground truth is taken in absolute terms. And then we compute the sum, divide them over the total number of examples we are running the test on, and that gives us the mean absolute error. So unlike mean squared error, you can see over here that the larger errors are going to contribute in mean absolute error, but they're not going to be penalized out of the way. So it treats all errors almost equally. And relatively, this is more robust to outliers. So if there is a chance that you might have to experience outliers during your entire evaluation exercise, then mean absolute error could be a good choice. Okay. One more evaluation measure is called R square score. This is essentially the measure of goodness of fit, and R square is computed as using this formula. Let's try to interpret different components over here. So if you look at the numerator part over here, this is sum of squared errors. Y hat is the prediction, yi is the ground truth. And if you look at the denominator, so yi is the individual ground truth, y bar is the mean of the ground truth. and that's also squared. So this measures how much variance is explained by the model. So if we try to, if let's try to interpret both of the extremes, that when will it be an ideal score? So if you think of the maximum possible value of r square, that is going to be 1. So 1 can be achieved only if this term becomes 0. How will it become 0? Because if there is no error, if all yi's are equal to yi hat, that means that's a perfect ideal model and there is no error at all. So in that context, the numerator part will be 0 and will be ending up into value 1 for r square. So that is a kind of situation where we are talking about a perfect fit or ideal model. Okay. The other extreme is that this component increases to an extent that it approaches 0. When we say this model approach, this increases to an extent that the entire r square approaches 0, that means that this term is approaching 1, and which essentially means mathematically that numerator and denominator are getting closer, which means that your predictor is actually predicting the same output as that of the mean of the entire output vector. So all predictions are getting closer to the mean, or theoretically, if all predictions are exactly at the mean of the output column, then numerator and denominator are going to be equal, making this term 1, and 1 minus 1 is going to be 0. So that is going to be the other extreme of uh, this metric. Okay, now let's have a discussion on the evaluation metrics for the classification tasks. We had actually a quick go through of these measures, or some of these measures, when we were talking about Bayesian classifiers. So let's go over that part again. So configured matrix is a matrix which is created primarily for, so the default setting of configured matrix is for a binary classifier, but we can always extend this logic to a multi-class problem. So this is a 2 cross 2 matrix. On one side, we have actual positives and actual negatives. On the other side, we have predicted positives and predicted negatives. So when we start running the evaluation process, when we start running that test process, so we start with these four variables. TP is true positives. True positive means that the example which was actually positive has been predicted as positive. False positive means the example is being predicted as positive, but this is false, which means that actually it was negative, but we are predicting it as positive. False negative means that we are predicting it as a negative example, but actually it was a positive example. And true negative means that our prediction says negative and actual label of the class, actual label of the instance is also negative. So these green boxes are essentially the correct predictions, and pink boxes are the predictions which are off the target. So the way we start from the programming perspective is that we create these four variables, TP, FP, FN, and TN. We initialize all of them with 0. And so let's say we have to run our test exercise on 10 examples. So as the first example comes in, we actually, because this is part of the test data, so we know the true label of the example. And we pass that example through our classifier. So classifier will be outputting something as positive or negative. So depending on the prediction and depending on the actual label, we place our newly tested example in one of these four boxes. Right. So for example, if it was actually negative and our classifier is saying positive, so we'll be just incrementing this box. We'll be incrementing this variable in our program, which is false positives. And with every example, with every test example, exactly one of these variables is going to be updated. So if we had like total 10 examples, so then the sum of all these four boxes at the end of the test process should be 10. So once we have these four variables computed with us, so we can have an intuition that if there are more values in the green boxes, then that gives us a like good indication or good feel about the performance of the classifier. And if the numbers in the pink boxes are dominating, then that's a weaker feel about the performance of the classifier. So we define different evaluation metrics based on this confusion matrix. So the first evaluation matrix which we define is called accuracy. So accuracy is essentially the proportion of true predictions or correct predictions out of the entire pool of predictions. So TP and TN, the elements which are on the green diagonal, they are added up and we divide it over the sum of all test examples. The total pool of the test data is its count goes in the denominator. So the denominator is sum of all those four boxes. We define another evaluation matrix, which is called recall. Recall essentially measures that how good is our classifier to recall the positives. So if there were some actual, there are like actual positives, and our focus is on all actual positives. So we are interested in computing the number of true positives out of all positives which are given over there. So out of all positives, how many positives have been recalled by the classifier will be assessed by this measure or metric, which is recall. The next metric is precision. So precision primarily measures the exactness of the classifier. It computes the true positives out of all positives which have been predicted, right? So all those positive predictions are put in the denominator, and out of them, the true ones are in the numerator. And in fact, these four variables are like the four variables which are in the confusion matrix, they are like very strong components of defining our own evaluation matrix as well. So we depending on the task or depending on the sense or the kind of insight you want to have from the entire evaluation process, you can customize the evaluation process, and you can define or choose a subset of the evaluation metrics which are more relevant in your context. Specificity is another metric which is computed from the confusion matrix. So in the numerator, we have true negatives, and in the denominator, we have true negatives and false positives. So which means that out of all negatives, we are trying to figure out how many negatives have been predicted correctly. Okay, so we have talked about accuracy. So in the nutshell, accuracy means that we are interested in counting the correct predictions out of the total predictions. So each evaluation metric has its own strengths, its own weaknesses. So as a machine learning engineer, we need to know that what kind of evaluation metric will be a good choice in a particular setting. So one bottleneck of accuracy is that it's sometimes misleading for imbalanced data sets. So take a pause. This is the first ICP for today's session. So if you took a pause, you might have figured out that a binary classifier always returns yes. This is a classifier which has been given, a very simple classifier, one line function, which always returns true on the test data. And at the same time, someone has reported its accuracy as 90%. The question is it possible? And you might have figured it out that yes, this is possible if your test data is imbalanced with 90% of the positive instances and 10% negative instances. Though your binary classifier is a very biased classifier, it only says yes on anything, irrespective of the features. So because the questions that you are posing to the classifier for assessment are biased. 90% of them are already positive, so it will say yes, and there will be a match. So our correct predictions will go up to 90%, and then there will be only 10%, 10% examples which will be misclassified. So 90 out of 100 will be the accuracy of this kind of classifier. So this accuracy might be misleading in the context of imbalanced data sets. We need to be careful about this point for uh, in our practical life. Okay, so if what is the kind of stuff which precision captures? Precision captures that how accurate are positive predictions. Recall is how many actual positives did we find, and specificity is that how well the model avoids false alarms. This is just for the sake of your information. There are like different terms used for the same evaluation measures. For example, precision is also known as positive predictive value. Recall is sometimes, in fact, quite commonly called sensitivity in literature, or we use the term true positive rate as well for recall. Specificity is also termed as true negative rate. Okay, another ICP, take a pause. So if you took a pause, you might have figured out that a binary classifier you designed to flag COVID patients is being evaluated. Which evaluation metric will you choose to assess the impact of your classifier? So you might have figured out that over here, the criticality of missing an actual COVID patient is very dangerous. For example, if your classifier fails to flag a COVID patient and classifies it as a healthy patient, that is going to have quite negative consequences in our real world. So in that kind of situation, you'll be going for recall because false negatives are going to be more problematic than false positive in COVID context. Another ICP, a binary classifier you designed to flag a spam email is being evaluated. Which metric will you go for? So if you pause the video, you might have uh, figured out that over here precision is more important because false positives are going to be more problematic in this context. By positive, we mean that whether the mail was spam or not, right? So we are like, if it is a spam mail, we are calling it positive. False positive means that if there is an important email and which means that's actually not a spam, but your classifier says it's positive, so it's a false positive, and that is going to uh, be a problematic thing in our real world. We might be missing or delaying response on something which has actually gone in our spam folder. So we'll go for precision over here as the metric. So F1 score is a commonly used score, which is a harmonic mean of precision and recall, and it is computed using this formula: 2 times precision multiplied with recall over sum of precision and recall. So when both of them are important, F1 score actually is a good choice, which gives us a balanced view uh, between precision and recall instead of choosing one of them. Okay, so in our like classification setting, uh, our model generally in the context of probabilistic classifiers, our model outputs the probability of X being a member of a class, a particular class. So what we do is that we convert this probability to class using a threshold. So commonly we use 0.5 as the threshold for binary classification. So let's say we use this term tau for notating the threshold. So our class is going to be 1 if the probability is going to be greater than equal to the threshold. Otherwise, it's going to be 0. So if we change the threshold, we know that we might be ending up two different classifiers. So if we lower the threshold, if I go back to the previous slide. So if you focus over here, we are essentially thresholding on the probability, right? So when we say if probability is beyond the threshold, is greater than equal to the threshold, it is being classified as the positive example. Zero means that it is going to be classified as the negative example. So if we lower the threshold, then the chances are that more positives will be predicted. If more positives are going to be predicted because of lowering the threshold, then our true positive rate is going to go up. And at the same time, false positive rate is also going to go up because our predictions are going to be more positives because of lowering the threshold. If you go for a higher threshold, if we increase the limit, if we increase tau, for example, we make it like 80%, if the probability is greater than or equal to 80%, then we will be ending up into more negatives being predicted or fewer positives being predicted. If fewer positives are being predicted, then our true positive rate is going to go down. And consequently, false positive rate is also going to go down because our entire pool of positive predictions is going to shrink. So the trade-off is that catch more positives versus avoid false alarms. So what we do is that we use a curve, which is commonly known as ROC curve. ROC stands for receiver operating characteristic, a term originated from some era of World War II, but is very commonly used over here in the machine learning literature. So ROC curve plots true positive rate versus false positive rate against different thresholds. So a quick recall, that true positive rate is that out of all actual positives, how many did we correctly classify? And false positive rate is that out of all actual negatives, how many did we incorrectly label as positive? Out of all actual negatives, how many did we incorrectly label as positive is called specificity, and you might be able to recorrect these terms, that specificity is actually sum of specificity and false positive rate is one, right? Because in the context of false positive rate and specificity, our denominators are same. So out of the same pool, we are talking about true negatives and false positives. True positive rate measures how well we catch positives. False positive rate measures how often we raise false alarms. Okay, so in the ROC curve is a curve which plots true positive rate versus false positive rate. So we compute the area under this curve and we call it AUC. So AUC, this area primarily represents the probability that model ranks a model ranks a random positive higher than a random negative. So what does that mean? So in the context of a perfect classifier, this area approaches 1. For the random values, it has to be at 0.5, and uh, higher curve towards top left is better. And what do we mean? How do we interpret these things? Let's try to have a look at these visualizations. Okay, on one axis, we have false positive rate. On the other axis, we have true positive rate. So let's say we have this red line is essentially the ROC curve. And this particular visualization is representing an ideal curve where true positive rate is always uh, very high. And as we even move towards right on the false positive rate, we don't compromise on true positive rate. So the area under curve over here is actually this entire shaded area, which is a perfect square, and each side of the square is one. So area over here is one. So when AUC is one, this is one ideal extreme where our classifier is doing the ideal job. Okay, let's have a look at another possible ROC curve and its and the area under it. So if you look over here, this is primarily the ROC curve is between 0, 0, true positive rate is 0, false positive rate is 0, and then it goes to 1 with different splits, with different thresholds. So the area over here is half of the area of the square, which essentially means that area over here is 0.5. And this kind of uh, ROC curve primarily represents a random guess, an arbitrary classifier, uh, which could be the lowest possible benchmark, right? So any valid, reasonable classifier should be doing better than that, which means should be having area more than 0.5 under the curve. And if you look over here at this example, this is a slightly better classifier view of in terms of the area under curve, because area under curve would have been 0.5 if it would have been a somewhat like very close to a right angle triangle. So this, if we are going on this side, so that means that our true positive rate is increasing. And so the kind of curves which you might be having over here or here will always be the ideal kind of curve. So if our curve is bending towards this top left corner, so that always indicates good performance, right? So ideally, it should be taking shape of that square which we saw at the start. So choosing the right metric in a particular situation is important. What we have seen in this session is that mean squared error penalizes large errors. Absolute error is robust to outliers. And classification for classification tasks, accuracy is a good choice if you have a balanced data set. Otherwise, we should go for precision or recall depending on the situation, or we might be going for both of them using F1 score. And we can use ROC curve or area under curve to have a like deeper view of uh, false positive rate and true positive rate. So so who will decide that what kind of evaluation measure is going to be a good choice in a particular situation? Primarily, it depends on the problem domains, on the applications which we will be modeling. So if you have to predict price of a house, then RMSE is a good choice because it will help in penalizing the larger mistakes. So in the context of temperature prediction, small deviations matter uniformly. So you can go for mean absolute error. Financial forecasting, again, larger errors are going to be very costly. So mean squared error is going to be a good choice. So it depends whether you want to penalize the errors or not. If you want to, then go for the squared option. Otherwise, you can just go for the absolute one. In the classification setting, so for example, if our task is to write a spam detector, then false positives are problematic. Important email can get marked as spam and we might be missing it altogether. So we need to focus on precision. If you are diagnosing a disease like COVID, false negatives are important because sick patient will be missed out from the entire process of isolation or treatment. Then we have to focus on recall. If there is an application of fraud detection in an online transaction system, so we need to catch fraud but avoid false alarms as well. So we might be going with a balance of precision and recall, and we'll use F1 score. Uh, you might be able to reconnect this to our previous discussion that F1 score is essentially the mean or harmonic mean of precision and recall. or like in a in your own way, you can also take a simple average of precision recall and you can define your own metric, which is average of precision recall, and you can use that as well. If the classification task is on a balanced data set, your classes are evenly distributed in the test data set, then accuracy could be a good choice, which will give you a reasonable insight. So we are pretty much done with these practical aspects of applying learning algorithms. In this entire setting, we talked about different perspectives. The first one was that we started with bias and variance in this entire module. And we talked about underfitting, overfitting. Then we talked about how to do validation. We talked about different cross-validation techniques, different types, different possible subsets which we need to create from the given pool of data. And then we also talked about that how to evaluate a model which has been built, and why this evaluation thing is important, because if we have to ship a model for practical purposes in the real world, then we need to have a reasonable level of evaluation or a reasonable level of trust on the model before it goes for the actual unseen data in the field. So having a good know-how and good intuition behind these evaluation measures is an extremely important thing for an ML engineer, because by the end of the day, you will be the person making this decision that what kind of evaluation measure is going to be a good choice in a particular situation. That's it for today. Thank you very much.